Okay, so recording is running. So let's continue. Today we will take a look on, so unless there are any questions with regard to function calls, then today we will take a look on memory management, exceptions and strings. And since we want to start with the simple things, I would suggest we start with exception handling, because that is still a more low-level thing. Then we'll take a look on memory management, and finally we'll take a look on strings, and then we'll see how much time is left if we can start using our knowledge to something useful, or if we have to move it for the next lecture. So, oops, that was the wrong button. File, new project, console. So, as you may intuitively grasp from the name of exceptions, an exception is something that usually should not happen, and generally exceptions are thrown on a hardware level when something happens that should not happen. So for example, if you would try to access a memory region which is not valid, then the hardware of the CPU would raise an exception, and then the operating system's exception handler would inspect what happened and then probably terminate the application. Of course, it might not always be desirable to have your application terminated on an exception, so there is a set of mechanisms that one can employ to mitigate such situations. Of course, aside of the obvious one, avoiding exceptions, there are mechanisms how an application can register an own exception handling, such that before the operating system will terminate the application will be able to do some own action, even and often just say, okay, just ignore that exception and continue execution. Of course, the execution usually cannot be continued where the exception was, or where the exception originated. On even very special cases, one might leverage the capability of actually resuming at the very same position. That would usually include that the application would then rewrite something in memory and modify the code that was executed. So such more exotic uses of exception and continue mechanism is rather used by, for example, some copy protection schemes where the program would intentionally contain invalid opcodes, and then once the application runs into such opcode, the exception handler routine would then rewrite the opcode to what it really should be and then continue the execution. In pretty much every other reasonable use case of exception handling, the mechanism is used to, when exception happens, execute some exception handler which will print an error message or something and then terminate the function in which exception happened gracefully, instead of actually resuming the execution where it broke the first time. And this way the exception mechanism can be actually quite useful. So in C++, which we will take on a look later, the exception handling mechanism is even more advanced than the normal just C exception handling, but it generally is quite useful because an exception can be thrown through multiple level of function calls. So you can have a function that calls a function that calls another function, and this function throws an exception, and somewhere at the beginning of your call chain you can have your exception handler, and then the exception thrown somewhere deep inside your call tree will terminate at the exception handler in your application. So this way you can, for example, when you have scenarios where you are actually always supposed to return a valid value which would later be used for something. For example, you have a function which is supposed to return a valid pointer to something, and it is not supposed to return a null pointer or an invalid pointer. Then you could use such an exception mechanism to prevent your application from continuing execution with an invalid value, or at least trying to do execution. You could on purpose throw an exception inside your function when you notice that you cannot return a valid value, and then somewhere higher up in the call tree an exception handler would then catch this exception. So let's try implementing our first exception. So we have of course our main function. Let's start start the try statement. So exception handling is always started with a try statement. So everything inside the code block after the try keyword will be guarded by the exception handler. And there are a few differences between C and C++ exceptions. So in C, you are much more limited with what you can do, and you start your try statement with these 2 underscores, which might appear a bit unintuitive. In C++, you just write try without the underscores, and the syntax and the behavior of this mechanism is quite different. So we will see that later today, how the other one looks. Then we can have some code inside that does whatever. So we can write here whatever we want, and then at some point, when we want to, when we are done with our code block, we write except, and then this is our exception handler. And as you see, it is underscoring here red because it expects a some statement inside the brackets. So for this statement, we need to actually create a function which returns an int value. We call the function filter, but we could call it whatever we want, and it takes a unsigned int code as first argument, and unsigned, and then it takes a struct exception pointer's exception pointer. The structure is defined in except h, so we can actually maybe add some includes first. Let's include stdi also, with that we can print to console and include Windows. That might be useful as oops, typo, Windows, and include except h, where the actual definition of this structure, this x was also abbreviated thing like this, yeah, where the actual definition of the structure, so we actually don't need to tell it that it's a structure. Why do I have a typo? I'm missing an I pointers. So we can look how the structure is defined. So we have here another structure. It contains even more data, so it's quite a complex structure in total. And context is just this thing here. So the context is the state of the entire CPU at the moment the exception happens. So if we would want to resume execution, then we would of course need to know what the registers were when the exception happened, and these are captured here in this context structure. So in principle, once we enter this filter function, we have all the information we might ever need to handle the exception in whatever way we want. And this function can well, evaluate the exception, think about what happened in case of the aforementioned DRM scheme, rewrite the application code to correct the intentional mistakes. But usually what it will do is it will just return execute handler, which is one of 3 values that are valid for the return. So these are the other ones. So except execute handle means it will execute the content of the code block here. Returning continue search would pretty much just pass hand out, let the operating system or the next level of exception handling. You can have, by the way, multiple level of exception handlings nested. So here it would just invoke the next level of exception handling, and if there is no level that you have defined, this would then invoke the default operating system exception handler that will then terminate the application. That said, one more comment on this. When I say that you have exception handlers in your application and the operating system has its own exception handlers, The way this works on a low level is that every exception will invoke the operating system's mechanisms, just that they will then either pass the control to your exception handler or to its own. But at the core of the mechanism, always the operating system will be invoked. So this mechanism invokes quite a few context switches and usually does not have a great performance. So if you are writing an application and you want to return exceptions, in rare cases it's fine, but I would avoid trying to use exceptions as a regular means for your application to implement any sort of control flow, simply because this will complicate things and make the performance of the application not as good. Of course, in case of a rare exception where something bad happened, one-off events don't really count. They can be as slow as you want. It will not negatively affect the performance as long as they are rare. So let's add some comments here. So this one, and the second one is okay, so we need to, of course, call the function in our statement here, and then we also need to somehow pass the arguments to it, so we can get the use the getExceptionCode function to get the exception code, and we can get exception information to get the exception information, so the exceptions pointer here. And so that we see what is happening and what is not happening, let's add some printf function calls. So as I think I already mentioned, the printf function allows you to just write text to the console. Start. Then here we will just add another one. So exception filter function, and here insert exception handler code. Okay, and then we will add something here. The try block, and now we need some exception. But before we do it, we should also add here a success message, and here maybe a finish. So success would be if we don't crash. So if we don't have an exception like this, when we run it, we will not enter the exception handler. We will instead just write start inside try block, success, and finish. And now we add some exceptions. So let's put our exceptions in their own function. So void divide by 0. So to divide by 0, we just define two variables, and a third one, which we then just make x divided by y, and here we have our division by 0. Then when we call the function, instead of start inside try block success, we will see start inside try block, then exception filter, and then inside exception and the code, and then finish. We will never arrive at success, since the exception, as we see here, was thrown and we could not resume the operation. So there is no way to recover from that one. One could, in principle, if you would know the code very exactly, change the 0 in the memory to not be a 0 anymore, or change the register which holds the value to not be 0 again. So there are ways how we could recover from that, but it is highly unpractical. So if we would want to know that, let's say 0 will be already stored in the RAX register instead of read from memory, then we could in principle change the register in the context that I have already shown you. But if we then compile, for example, for a release build, or just use a different compiler, then the compiler may choose to use the RCX register instead, and then our code would just fail because at this point we are making assumptions about how the compiler will compile it, and those might change arbitrarily. So with a different compiler entirely, or just with a different version of the same compiler, the results might vaguely differ. And of course, if you just change between release and debug build, this might introduce such changes as well. So we are not going to do anything like that. I just wanted this to be mentioned for completeness sake. Then of course we can here, instead of invoking our exception handler, we can return exception continue search, and now the exception should be passed to the next level of exception handling. And in this case, as you see here, our debugger is like, it inserts itself before the operating system handler in the handler hierarchy. So the debugger captures the exception. The operating system does not kill the application or anything. It just tells us what happened. In this case, this exception code tells us that this is a integer division by 0. And then at this point, we kind of also don't really have an option how to recover from that. If we review the code, we see that EAX should contain 1, and then it should read from memory at position epsilon the thing. We could kind of tell it to continue, but it will then just, well, continue again. So if we may continue here, this is kind of equivalent to this continue execution, but as long as the error persists, it will always crash. Since we are in the debug and we know the exact representation which we have here, we could in principle try fixing that by hand. Just, oops, I think it did it wrong, +4. Wait, but this tells us that it's 0. It should be +24h. The wrong position. So here we have, well, 0, so let's make it a 1. And so that's a 10. A 1, and in principle now, if we continue, it worked. So it said success, and we have invoked like the exception filter like once. Then we could, because we pressed play, and I think I pressed play a second time. So as you see, in principle, there is a utility to this continue execution option, just that in reality, I mean, if you would really want this to somehow work, you could write a code that would look where in memory the error happened, and then try to disassemble the code in memory, and then somehow intelligently fix it, but that becomes quickly infinitely complicated. So the simple ways to kind of break your code is just to insert invalid opcodes at known positions and fix them, that you can do. Messing around with variables, that is not reasonable. We can of course try another exception, so we could try access something that has an invalid memory. So, yes? Yes? Yes. Yes. Let's run it again. So it's self-explanatory if you see it doing its thing. So we are here. So we have inside try block. Can't I move it? I cannot move it. That is annoying. Because this other bar is here. One moment, please. Right. So now we see everything. So the exception happened. We are here. The debugger caught the exception, and we at this point have entered this exception filter. So we entered this, and this thing tells then continue search. So it says I am not responsible. The next thing should handle it. The next thing to handle it is the debugger of Visual Studio. And now if we press continue, then we pretty much told it at the higher level, we returned this -1 value here, and told the CPU basically, or rather told the operating system to make the CPU repeat the last operation which already failed. And each time I press continue, the thing repeats. It's because the error is not yet fixed. If we would fix the error, basically by editing the content of y in memory to be non-zero, then pressing continue would make it continue, and then it would work out. At no moment here in this execution we will enter this this block here. this exception handler because this is our handler. This one we would only enter if we would have executed the, returned the execute exception handler value. Okay, you're welcome. So let's stop this. Oh, actually, let's repeat this. Let's put a, it was the wrong button. Let's put a breakpoint here. So that we also see that the code here is the same code that was shown to us by Visual Studio when we just made it run into the exception. Okay, so we wanted to dereference something that's null, so int asterisk x is gleich null, and then asterisk x is gleich, I don't know, 0, doesn't matter, 1. This will create another sort of exception. So for example, here we could say that on the divide by 0 exception we let the Visual Studio handle it, and on the dereference null pointer we want to handle it ourselves. So we could make this act dynamically, but usually there is not so much use in those things. Let's just comment this out. Okay, let's run it and keep the breakpoint here, or actually inside the exception function, comma null x percent null x. We can print the actual exception code to the terminal directly, so that then we don't even need a breakpoint to see what the exception was. Okay, so again Visual Studio caught it. Wait, it didn't print it. Interesting. Let's quickly see how this behaves with the other one. There are settings in Visual Studio that you can make it that it will break like first. Yeah. So as you see with the divided by 0 exception, it first invokes the block, and then only after we return continue search it gives the control to Visual Studio. But if we do the other exception, Visual Studio will be invoked directly, and it won't even give an opportunity to the built-in exception handler. We can disable that somewhere. Where was that exception settings? Well, I just disable all of them. Zack. So now it will only break on exceptions if they have been past top level. So now you see, even though we still did the dereference null pointer exception, first our internal handler was invoked, and only after this handler didn't find anything, then Visual Studio decided to take action. And this can be configured when you are attaching a debugger. Then the debugger can tell the operating system that if an exception happens, what should it do? Should it execute the exception handling of the application, or should it directly break and give control to Visual Studio or to whatever other debugger you may have connected to inspect the exception directly? This is quite a useful feature actually, because you might, if you are using exceptions, and then you see, okay, you end up in the exception handler, but then you might not know where you are coming from, so where the exception happened. The easiest way to find this, so of course you could try some more advanced ways, like getting the instruction pointer from the context structure and then going there and looking where the code is. But the much more user-friendly way is just you select the particular exception that happened in the exception settings that you have here in Visual Studio, to just always break on this exception even if there is a handler for it. Then you will be directly brought to where the exception happened, and then you can fix it, or at least understand why it happened and then fix it in some other way. So that's that. And there is one more thing that can be done with this try statement. So for now, well, let's leave that exception here. We can, first of all, as mentioned, we can wrap these things in multiple levels of exception handling. So first, let's do this. We have a function that's called test, which will have one level of exception handling, and we will then have our second level of exception handling, and filter 2, filter 1, and filter 2 will return continue search, and filter 1 inside exception filter 1 inside exception filter 2, and exception filter 1, the top level one, will execute the exception handler. So right, printf, we are missing a semicolon here, we should not write success here, just done. And here maybe also to illustrate it, enter test and leave test. Then we have start and finish, and then what we will see when the exception hits here is that while we enter the function normally and print this line, and then our filter here is invoked, this line won't happen because we say continue search, and we will not have this leave test here either. So this already kind of indicates that if there are things on the stack set up that some of the stack's content needs to be rolled back such that this function here would be able to continue execution correctly. So this already indicates that there is quite a lot of program logic behind the scenes, since, as we mentioned already last time when we looked into functions, some registers which are used within the function's execution are defined as non-volatile, meaning that when you invoke a function, the invoking function can assume that once the invoked function terminates, some of its own, so the invoking function registers will remain at the values that they were before the invoked function got invoked. So in such case, if we would just redirect the control flow directly to our code block here, those registers might not have a valid content, but they have a valid content. So it means that the operating system, or at least the C runtime inside your application, is walking the stack back and then restoring the important values such that you can continue from this exception without any problems. So let's try this. Suck. Okay, so we start, or maybe we should here write start main. That looks nicer. Okay, we start, then we enter our test function, then we enter our try block, then we do some bug, and the exception filter 2 returns continue search. So then we jump out of the function directly to the next exception handler, so this one, exception filter 1, which then, okay, it sees same exception, but this time we set it up to execute the handler, which it does, executing handler, which is here, and then this function, this main function, then terminates gracefully. Trying to debug this mechanism of restoring the stack is difficult, if not outright impossible, because in some way a good portion of these operations will be just done by the operating system itself. So this way we don't really need to, we don't really have the opportunity to put breakpoints and inspect what the code is doing. Some of the functionality is implemented, so we can, for example, have here again a breakpoint. We can look how the call stack would look. So in this case, so we start, of course, in our main function where we then call test. The test calls our bugged function, and then from here, what basically happens is the key user exception dispatch function in the anti-DLL DLL gets invoked by the operating system, which then invokes yet another function, which invokes another function, which then invokes yet another function inside the C runtime. The C runtime is a collection of libraries, I think I mentioned that already, which is just invoked at the start of your program, and also that implements a lot of basic functionality that in every C application one will expect to find. I guess if we click here on load symbols, we will probably get them. And then we get the name of the function. In this case, it's the __c_ specific handler which got invoked, and then this handler then jumps to this small code section where we invoke our function, from which then our function is invoked regularly. So as you see, there is quite a significant amount of additional logic that takes part in this whole mechanism, such that everything works out. And all this code, we don't need to care about it. It is implemented on Windows by Microsoft, and if you would use this mechanism on Linux, then by the Linux developers. So obviously everything here in between would look differently, because the C runtime on Linux is completely different, and they don't have any NTDLL. They would just use the C library instead, and so on. So those things would be different, but the code, your code as provided here in this example, would work pretty much on every platform that supports C++ out of the box without any platform-specific changes. Okay, that much to that. And one last thing, the try block can also be used to implement additional functionality. So for example, here let's add another try block. Of course, obviously you can have try blocks inside try blocks inside other try blocks. How to say it? Try blocks inside try blocks inside other try blocks. Not just nested in function, but also multiple levels of this try block thingies inside one function. Usually that is not something that is used past two try block instances in one function, simply because usually you can just do everything with your filter. But what you cannot do with the filter, at least not easily, is the other keyword other than except. It's called finally. And the way this works is that as soon as this code block terminates, for whatever reason, whatever code in this finally block here is placed, it will be executed. And this is quite useful for different cleanup operations. So in this case, we will just print f, and what do we write there? It's final termination. And then we write here. There is like the functions get exception code and so on. There is a function called abnormal termination, which is true if something abnormal happens. So as you might remember, the trinary operator, we can use it here to switch between two strings. Termination, yeah. And so depending how we exit from this code block, we will either get here a normal or an abnormal termination signal. So let's run the function here again. Alright, we don't want the breakpoints, so let's exit from the breakpoints. And here, so the code flow was like this. We enter the function, we print the first thing, we print the other thing. Sorry, we were here. We enter the main function, we print the thing, then we have one try block, the second try block, then we invoke test, which then prints something. It says its own try block, so we are now at this position here inside try block. Then we do our exception. We invoke this exception handler, we don't invoke this. Then from here, since the exception happened, we end up in this line. We invoke the filter 1, which then tells us to do this. And once this is done, so this but respectively, so first the filter is done, then after the filter has returned whatever value it wanted to return, this finally block is invoked. So we see it here, and once this finally block has been completed, then here our exception handler is actually being executed. This might be a bit counterintuitive. One would maybe think that that this block is executed last, but no, it's executed before. And the reason is because we might want to clean up things. So if you would go to executing this code block, then everything from this call here would have already been torn down, the whole stack and so on. So if we put the breakpoint here, we also see that we are just in the main function. So on the stack there is no trace of our exception, our call to test or anything. We are just in the main function, and that is it. Hence we need to invoke this finally block first, because this finally block, we could of course have it on the level once higher. So we can put another finally here. You can have multiple finallys, that is obviously not a problem. Then let's indent this. So here is finally, it's main finally. No, it's finally in main, and here we call it finally in test. Then we'll see that first the test finally is invoked, and the main finally is invoked, and then the exception handler. And obviously if we would tell the whole code to execute this exception handler, then test would successfully finish, and then of course we would just print success and not invoke any other exception handlers. The normally exception handler would always be invoked, so we can take a look on this in a second. So here we run. Okay, we don't need the breakpoint here. So we have our first filter which says continue. The second filter, so it's the second filter which says continue. Then the first filter which says do the exception handling. Then we have those two finally blocks being executed, such that the functions can clean up whatever they want to clean up. And then we are inside the exception handler block, at which point our control flow in a way already has exited the exception handling mechanism, and we are just inside our function at a certain offset executing code. So at this point we can now change our second filter to execute its own handler. So here inside exception handler in test, and here we will add call this one in main, so that we have different. So if we run it now, we will see that it behaved slightly differently. So we enter, we are here, then we have our exception, then we invoke our filter number 2. It decides it wants to handle the exception, then finally 1 is executed, finally test, termination abnormal because an exception happened. Then we are inside the exception handler in test here, and then from here we just continue execution as normal. We just then print leaving test, then we print here success, and then we, after done this, arrive in this finally statement, because as mentioned we always arrive in this block, and then finally in main terminated normal. So everything was fine, and of course there was no more exception handling, this was not used, and we then here end up in printing our finish message to the console. So you might wonder what this finally could be useful for. Generally, when working with low-level languages like C, C++, so on, you often allocate various system resources. So be that system memory, or handles to files, or handles to some other objects. For example, on Windows we have GDI, window handles, and others. So there can be quite a few different objects that an application can open a handle to. And since it is a low-level language, once you are done using whatever resource you have acquired, you need to tell the operating system that this resource can now be freed and probably destroyed. So usually in your code this would always be part of your cleanup procedure. And if you have an exception, if you throw an exception, then you kind of interrupt the normal execution of your application, obviously, and then such references which you have acquired but never freed would accumulate, and at some point the operating system would say, well, that is too much, I will kill that application. I can only give out 1 million handles. That is excessive. 1 million handles is excessive. But at some point it will just the operating system will decide to kill the application, or in particularly worst cases, the operating system will allow the application to continue. It will just start not working, the operating system in total. So we have here this nice task manager, and in the bar at the top we have some of the resources listed. So obviously memory. So if your application uses up all the memory of your computer, it will either become unusable or at least extremely slow. That's obvious. But then we have here these objects, actually 2 of them, GDI objects and user objects. These are Windows resources which are limited per desktop and are related to all the graphical stuff that happens on the screen. And if those objects are exhausted, then applications will open empty windows or not open windows at all, or Windows will be missing some of their control elements. It is not pretty. And obviously the operating system will not automatically kill some applications, even though that actually might be reasonable. Here you can actually sort by the amount of these resources used. So you see actually the Windows Explorer is using quite a few, as well as Visual Studio. Yeah, other resources which are limited is the amount of windows that you can have. So in this case we have here less than 500 windows, which is okay. My host system I have 3000 windows, and well, here we are below 2000 objects. On my host system I have 25,000 objects. So the limits, we are here not even close to the limits, but they are limited. And with handles, as I mentioned, file handle and so on, here we have below 80k on my host system, below 500,000. So actually 1 million handles would not be that excessive, and if you don't have this tool, you can at least inspect some of the resources. I think at least you could in the old version. Yeah, so if you go to like the performance of your Windows 10 or 11 Task Manager, then when you look at the CPU resources, it will also give you the amount of processes and threads running on the system, as well as the total count of file handles open. So this is a interesting information. And what I wanted to say initially, you can use this finally block here to release those resources even in a exception condition. And once we start using C++, we will learn that this mechanism is automatically leveraged to clean up C++ objects which have been allocated on the stack, which gives you a huge amount of power with regard to managing your resources automatically. But that's something for the C++ part of the lecture. So this much about the normal C exception handling. I think I covered everything that is worth mentioning at this level. The C++ exception handling we will take a look at later. Maybe one thing to say about the general differences here, we actually kind of did have to cause an exception on purpose. We could actually try writing an exception manually, but for this we already need to create an exception record. So in C, in plain C, it's not intended that you really use exceptions as a integral means of your mechanism. You just want to be able to handle them if they would happen, but you don't want to cause them like on purpose. So if you go back to my earlier example where you have a function that returns a value, then the C approach would be that that you always have to check the return value, and you always reserve in the way you design your system for you the option for your functions to return an invalid value. So for example, if you are returning a pointer, you would always return null instead of throwing an exception to indicate that whatever was to be done, the function failed. And on the level of C, this works great. Why with C++ this is a bit more tricky is because in C++ you can return not just pointers but references, and as we have learned, well, a reference is just a disguised pointer. Since we cannot directly access the value of the reference, only the thing it refers to, if we have a function that returns a reference, we don't have a means to return an invalid value. So in this case, the only thing we could reasonably do would be to throw an exception, and that's why in C++ the exception mechanism has been extended a lot, such that you can create your own custom exception objects. You can attach arbitrary information to your exception, so you can write entire messages, what happened, why it happened, and so on, and this information will be then available inside your exception handler. As said, on this we will take a look once we covered C++ classes and C++ objects and all these automated mechanisms in one of the upcoming lectures. For now, we only handle the C part of the exception handling, and at this point we are done with exceptions. So if there are any questions, ask them now. If not, then we can continue with the next important mechanism. So are there any questions? Okay, if there are no questions, then let's create a new project. I will minimize this and I will close that and create a project. We will call it memory. You have already seen the usage of memory with regard to the stack in functions, so the memory that your functions have always at their disposal. But as we might remember, the stack is quite limited. You can only allocated memory in the reverse order to how you allocated the memory. You cannot just take a chunk of memory and give it to some other function just forever. You could do it, of course, when you are within a call stack, because then the memory will remain valid. But if you would have a function which would remember this value somewhere else, for example in a global variable, and then you would try to return to this value, that would fail. So maybe actually we could implement such a test case. So we would need some, let's say, int asterisk g my int, g for global, but as already said many times, the names are arbitrary. There are a lot of conventions, and some people are actually quite militant about which conventions are better and which conventions should be used. Just as a comment on that side. So generally you have either the convention where you just write everything in lowercase with underscores, that's called a snake case, and the other convention is when you write it like this. So you can start with a small or a big letter, and then instead of using spaces, you are capitalizing the first letter of whoever you want to make some sort of break. So this is camel case, if I recall correctly. I might, but that makes sense. Like a snake is not standing out, so I think I'm not mistaken. And the other one is called like this for whatever historic reasons. I don't know. Never knew and don't get to remember. We will stick with this one for now, but I mean, this one looks prettier. This one is probably better to read, and this one needs more memory, while this one obviously saves a few bytes, but these few bytes nowadays don't matter at all. The better readability of this might be a reason to use it, because here you have really clearly separated the different words in your name from each other, while this just looks nice because, I don't know, historic reasons probably of my history, because that's how at the beginning I started out with this, and yeah, but all choices are valid, whatever you prefer, as long as the code works. It doesn't matter. You could also just call all your variables variable 1 to however many you have. That will be insanely unreadable, but will work as well. Anyhow, so we have here our global variable. This variable, by the way, the value null is assigned to this variable by the C runtime before main is actually executed. I'm actually not sure if we put a breakpoint here, if we would arrive at this breakpoint. Nope. It just moved down. So if we would have here like a more complex situation, like a function invocation, then we could definitely break on it. But we don't want to do that now. We could maybe do it later just for fun. But for now, let's just continue. So we make a function void set int pointer int stern ptr pointer, zack, and here we just set our global variable to be the pointer, and then we will get another one. We'll call it getInt without pointer, and it will return as a int. So it does not have anything in it. It just returns this value dereferenced. So let's first use it in a way that will not cause a bug. So int my int is 1, 2, 3. Then we set pointer, give it the address of 1, 2, 3. Then we int test is equals getInt, and then we printf my int value double point %d \n. A bit later I will describe in more detail printf and all this formatting here, so you have seen me using it without saying anything. It's because I will say much more about it later. I clicked on something. Right, so this will work, and it will actually work as expected. So it will just print 1, 2, 3. Did I print the comma? I don't need the comma. And now we will use it in a way that will break it. So let's have a function in my void my function 1f. And then we will just move those two things into this function. There is of course always the chance that it will still work just because we have not used the memory yet. So let's see what it will do, but I would hope that it will, yeah, it failed. So you see, the return value is not valid, and the reason is, so the value here, this pointer, lives on the stack. And as long as we are within the call tree, it is fine because it still lives there. As soon as we exit from here, so we exit this function, this memory that we have here becomes invalid. Of course, you might be very lucky that it wasn't reused, and then you randomly will get the right value. But much more likely is it will have been overwritten. Actually, it probably definitely was overwritten because I have not disabled all this runtime checks and all this debug stuff. So actually, the compiler will add code to on purpose overwrite all the memory so that you will notice that you are doing something that you should not. I guess if I disable that, we might end up in actually the code now printing 1, 2, 3. Yeah, you see, if we would have now here like a lot of code doing something, then we would also have the result in test in this memory having been overwritten by something. But since we didn't do this, randomly it worked. And this is the probably most dangerous thing about C++, that if you don't use all these debug facilities that modern toolchains offer you, that it is really easy to integrate bugs which will make your code work, but only most of the times. And this is like really a pain to debug. So using all these helping mechanisms, at least in the debug build, is highly recommended, because without them it's just a recipe for disaster. So okay, so we have learned that the memory on the stack does not survive past the exit of the call tree. So if we would have a complex program where we want to pass some memory block to something, how would we do it? Or another question, if we would want to allocate, let's say, a 1 GB block because we have a huge file with all of our measuring data, how would we allocate so much memory? The stack size on Windows is limited to, I think, 20 something megabyte. I don't remember. I should Google that. But it's limited, and you can change it. You can change the default value globally on your system, and you can also change the stack size when creating a new thread. So you could, if you know you will need a huge amount of stack, you could spawn a second thread from your main function, and while doing so, tell Windows to allocate some ungodly amount of memory of stack space for that thread. There is probably some limit where Windows would just then return you an error, but at least from a principal perspective, if it doesn't work on Windows, then just take Linux, and if Linux complains, rework the kernel to allow it, because physically you can have as much stack space as fits into your address space, and with 64-bit that is more than you could nowadays realistically cram of amounts of memory into a computer. So I think 64-bit has something exabyte, or not, probably even more. 2 to the power of 64 is a very large number. So if you could produce that much memory, which you might, I mean, big computers, big supercomputers, which are made out of just a lot of smaller computers, have ungodly amounts of memory sometimes, but that's prohibitively, at least financially, for a normal consumer. So the takeaway is that if you have a 64-bit process, you will never be limited, at least not within the next probably decade, by the size of your address space. Yeah, so that said, how would we reasonably, elegantly get memory which we can then pass between functions and which is not bound to our stack? And we do it basically on a most basic level by just asking the operating system to allocate a block of memory and give it to us. So that would be the most simple thing to do. So we could do it here. So instead of doing this, or let's change the example slightly. My int ptr is equals to reference. Right, so this is the bad case. Zack. And what would we do instead? So instead of doing this, what we can do is virtual alloc. This is the operating system function. This one is Windows specific. There is no virtual allocs on Linux. There is some other function which has similar arguments and does a similar thing, but it's not. So if you use virtual alloc, your code will not compile on Linux. That's the short takeaway. And we can actually even tell it at which address we would like the new memory to exist, but this parameter is more like a hint, so we can also provide just null so that the operating system will just pick a size, and then here we can tell it how much memory we want to allocate. So we could tell it, since it's an integer, we want 4 bytes, and then allocation type, I do not remember, memcommit, I guess. And flags, protection flags, mem read, no, I don't remember that. We want read write without execute. Was it page? I think it was page read write. Yep, that's okay. Now page read write execute write. That's the right one. So this one tells the operating system where we want the memory to live. So whether it will like to page it out to disk, or whether it will always keep it in RAM. We also need to cast here because this thing returns us a void asterisk, so this doesn't work. And then of course we tell it how this part of memory should be protected. So whether the memory should be readable, writable, whether it can be executed as code, and so on. So if we take a look on the defines, we have quite a few here. So we can have execute, just execute, so it can be executed but cannot be read. We can have execute read, execute write. There's also this execute write copy, which I don't think we can actually use on in a user level application. The idea with a memory with this protection is that, for example, if you load a DLL on Windows and then you have one application that loads this DLL, then obviously the application will need to have a copy of this DLL in its memory. But then you might want to have another DLL, another application which uses the same DLL. So ideally you would give it just the same memory, but this would mean that if the first application would be allowed to modify the DLL, then it would change the code for the other process, which would be a huge security risk. So what the operating system does is it marks all the pages as only executable, and if there is a write attempt to these pages, then for this memory page, the operating system will copy the whole page and allow the application to modify this copy, but then this copy will substitute the original page in the memory space only for this one application, while the other application will still see the original unmodified memory page. And what are memory pages, I guess, is the next thing I should explain. So first of all, here we told the operating system to allocate 4 bytes, but actually what the operating system can do is only it can allocate individual memory pages. So in this case, a typical memory page is 4 kilobyte. So if we would use malloc, if we would use virtual alloc for however little memory we allocate, we would always waste 4 kilobyte of memory. So this would not be good, and we will see a bit later how we can use mechanisms offered by the C runtime, some of them which are standardized across the C language so that they are available on Linux, and some of them which are Windows specific, to avoid this problem. But now to the question, what are memory pages? So any modern CPU uses a so-called virtual address scheme. So a physical address scheme, our physical address is basically where your memory addresses directly refer to one physical memory cell in your computer's RAM. So if you have like half a gigabyte, or no, that is not enough. If you have 16 gigabytes of RAM, then every of these individual bytes is individually addressable by a number. These numbers does not need to be consecutive, so the memory space might be split apart, because usually you would want to have some memory in the below 2 GB region, then above 2 GB you would have memory which is mapped to hardware devices, so that when you write to this memory actually change parameters in hardware, like in your SSD controller or your graphics card, and so on. And then usually all the space above 4 GB is then used only for memory, and devices are not using it. Although on modern systems you can enable above 4G decoding, which actually is useful for the new Intel, what's the name? How they call it? The new Intel graphics card, Arc graphics cards. They because what you can do there is you can have your entire 16 GB of GPU memory mapped into your address space, such that your computer can access the memory of your graphics card directly. This is quite a nice. This gives you quite a nice performance boost. What was done usually without, if you don't have this above 4 GB decoding, the mechanism which is used to access the GPU memory is called banking. So there you just map a small window of the memory into your physical address space, and then you can access only this small window, and then you have to write somewhere else in your address and then move the window to another portion of your GPU's memory, and so on. So through this window you can still access any address inside the GPU memory, but this is a bit a detour. So what we are basically interested in is just the fact that you have these hardware addresses which refer to your hardware, be that hardware or your RAM, and using those addresses, if you could use them directly, would of course be kind of not great for your applications, because then every application could modify not just any other application's data in memory, but it could also directly talk to the hardware and do whatever it wants. And operating systems like this existed, like the very, very old disk operating system called DOS, where you basically had no protection. They just run in real mode using real addresses, and if something went wrong, then the whole operating system crashed. And of course, since this was not good, smart engineers invented a virtual memory, or also called protected mode. So sometimes it's also referred to as protected memory. And the idea here is that every application in your operating system running on your computer will get a completely own address space. So it will get for example, on a 32-bit system, since we want to use numbers that are easy to pronounce, the total size of the address space is the 2 to the power of 23, so 4 GB, and the application will get an own window of usually 2 GB usually from 0 up to 2 GB for its own exclusive use, and the other part of the memory window from 2 to 4 GB will be reserved for the operating system kernel. And the way this works is the application can usually not access anything past this 2 GB barrier, except when the operating system would say, okay, this particular page here in my half of the address space, you are allowed to access this, and then the application can access it. And this access controls are implemented through a multi-level page table mechanism directly in the CPU. So the CPU has memory protection, a built-in memory protection unit, which ensures that an application, first of all, properly translates the addresses of the exclusive address space, and then that the shared address space with the kernel, it can only access those regions that the kernel has marked as explicitly accessible. And the way the whole memory, why it's called not just protected but virtual memory, works is that within this entire 4 GB of address space, there is no fixed relation between a address and the actual between a virtual address and the actual physical address on the RAM or in a hardware device. So the way this works really is that when setting up this page table entries, the operating system will say, okay, so at address 0xFF, you now have a page which is located in the physical memory at 0xAAA3 or whatever. So you have a full translation of virtual addresses to physical addresses, which happens completely transparently in the CPU whenever any instruction is executed. And this way, every application on Windows will get its own address space. So, for example, if you have this aforementioned DLLs, at the beginning, both applications will have this DLL mapped into the same region of their virtual address space, and this both regions in their virtual address spaces would then correspond to one physical region. But as soon as one of the applications would decide to change its own memory space, rewrite something inside the DLL for whatever reason, then those individual 4K pages that the application tries to write to would transparently be switched for other pages somewhere else which contain initially just a copy, and then the change is applied. And this mechanism, by the way, is also using the exception handling mechanism of the CPU. So as soon as your application would try to write to a memory region which it is not allowed to write, this triggers an exception, and then the operating system's exception handler, on which first inspects every exceptions, looks what happened. It looks up, okay, so this memory, it should be allowed to write, but it is not allowed to write because this memory is shared with some other application. So in this case, I'll make a copy, remap the page tables, and then tell it to continue. And in this case, this continue instruction, which we have seen earlier, is very useful because it allows the application to seamlessly continue as if nothing would have happened. And in another scenario, of course, when it tries to access a memory where it was set that it should not be able to write to, and for whatever reason, then only then this exception would then be escalated to the next and next and so on level of your own exception handling code, or of the exception handling code of Visual Studio, and ultimately again back to the operating system when it would say, okay, no one handled this error, so it's time to close the application. And well, and that's not even maybe it's the half of the story, but it's still there is still a lot of things to say about these paging mechanisms. So, for example, what you can do if you have this virtual address space is you can have a region of memory which is which was set up such that your application should be able to use it, but which at some point in time will stop being referred, being pointing. My English is not good today. To a valid address in memory anywhere, but just point to nothing. And this actually happens quite often. So if you don't have enough memory in your system and are trying to run more application than fits in your memory, what your operating system will do is it will check, okay, which memory regions recently have not been used, and then it will just copy them to your hard drive, or rather nowadays onto your SSD, and remove them completely from memory. It will remove all references to the addresses and just mark that those regions have been paged out. And then when the application tries to access such a region and causes an access exception because the CPU hardware sees, okay, this region is marked as not having a valid physical address, then the operating system has to do something, and then the operating system will see, okay, now the application tried to use this memory, so let's just find some free memory somewhere in the physical RAM, copy the memory which has been paged out to disk back to the real memory, and then update the address in the page table to point to this newly allocated memory block which contains the old data, and then it resumes the application. And if I recall correctly, the old Windows Task Manager even showed the count of page faults per application, and basically every page fault is whenever an application tries to access something in memory and this access fails, whether that be because this memory region has been paged out, so moved to disk, or whether there was something other happened, like for example it tried to modify a shared region of memory, but one which is not shared as read-write, but is shared as write copy, so that it makes a full copy on write, basically. So let's see if this we can see this somewhere nowadays. It might have been removed because they have reworked the thing completely. Spalten auswählen. Oh yes, and in German this is called Seitenfehler. Here it is. Seitenfehler, wait, Seitenfehler. So as you see, there are a lot, and so this false, even though here this VM has, how much memory does it have? Well, we are not even half full with the memory, but it still has a 2 GB paged out to disk just in case. So the operating system is kind of proactive in this sense that if it really thinks that some memory will really never be used for anything, then it just moves it off disk. And hence this amount of page faults in any system will just always be well, it will always grow and be just bigger and bigger and bigger because it's just counting up those failures. But it's not a real failure. It's kind of, this failure is intentional. It's part of the normal operation of your system, of this virtual memory mechanism. And the most fancy thing about this memory management mechanism is that you can even use it to do very exotic things, like you can, for example, map an entire file from disk into memory directly. So this, of course, is very operating system specific, so I have no idea how to do it on Linux, but on Windows there are API calls to do this. We will not trying this out. It is just good for you to know that if you would at some point in your career want to write an application where you want to access a file, but at the same time you don't want to like open it and access it like normally by calling functions read at offset, write to offset, read at offset, write to offset, seek to another offset, read and offset, write at offset, and so on and so on. But you really just want to access memory instead, you can do it. So then basically this operating system will look how big is the file. It will find a region in the address space which is large enough to accommodate the file. On a 32-bit system, obviously that will only work with small files, and in fact you can have a situation in a 32-bit system where you have enough RAM and your application still returns not enough memory because you wanted a large consecutive memory region and your memory space was just too fragmented to find one consecutive region of the required size. But on a 64-bit system, the amounts of memory that you can have virtually is so huge that you will not run into such issues realistically. I guess one could maybe try to provoke it on purpose by allocating memory like in large increments with this virtual alloc, and then on purpose then asking for a huge block that will not fit, but well, one would not want to break one's own program like this on purpose. So the way this file mapping as mentioned works, it is you get a large enough memory region, and then basically the file is not usually even like started to being read. It is the operating system just knows this memory represents that file. And at this point it would not even consume real memory on your system because it would only allocate it for virtually in this virtual address space for the one application, and only as soon as within your application you will start accessing offsets in this memory region, it will first generate a page fault and it will see, okay, so this was at this offset, so let's read this 4K block from the file, put it into memory. At this point it will actually allocate real RAM, and then you just continue, and it will, and if you like allocate, let's say, well, open this file like this and then read from front to back through the whole file, or read it randomly through the file, but the point is you access every single page in the file. Then if the file is not big, it might reside completely in memory. If the file is very big, then the operating system will have already removed parts from of the file from memory again to ensure that you are not wasting memory too much. So in this case, I think it will also count this memory as paged out, but I'm not actually sure. This also changes sometimes because these informations are usually just provided for statistical purposes, so they can change. But some of this information, again, in the normal task manager under Leistung memory, under performance memory, you can see it. So you have like how much memory is used. We actually have even some memory compression, which I will not explain what that is. We see how much memory is actually still free from the 16 gigs that this VM got. Then we have here how much memory is like guaranteed, so how much can be used, and 18 is simply the sum of the total physical RAM plus the amount of virtual memory which is stored in the page file sys on your C drive. You can, by the way, move this file also to other partitions than C, so if you have a small C and not enough room and you want a lot of virtual memory, you can move page file to another partition. The only thing to keep in mind is that you want something that is really fast. And also, if you are using an SSD, writing a lot to a SSD will reduce its lifespan. So nowadays it is not great to have not enough memory. It's better to have enough memory, and then you can have a very small page file. Right, so what else do we have here? Then we have this method is a metadata. Yeah, so this is the little extent of what you can see here on the normal task manager. As mentioned, with a more advanced one, you can get much more information. You can have total page fault on the system, which is a lot, and so on. But anyhow, let's continue with this memory management stuff. So I think the most important takeaway at this point is that the memory management system is somewhat complicated, that it works in this 4 kilobyte page size increments. Although this 4 kilobyte is not like a God-given. This can be configured in principle when the operating system is starting up. So for example, the modern Mac OS on which uses the Apple Silicon is using by default a 16K page size. As long as I think they use the normal Intel Macs, they also just use the 4K size as the standard. But on Intel, you have in principle the ability to configure your page size on the operating system level. So in principle, you could make your own Linux which will use a megabyte page size if that's better for you. There are certain use cases where bigger pages are beneficial, and obviously you need less page table entries if your individual pages are bigger. So you can kind of save memory, but then on the other hand, you might lose memory through the overhead of not always using one entire page. But anyhow, let's now so we have here our value, our allocated memory, and then we can assign to it, so we can use it and assign to it something. And now if we run the code, it will work, because even though we have re-enabled all these debug things here, simply because this memory now lives completely independent from the stack. So it will keep living even if the thread terminates. Of course, once the program terminates, the operating system keeps track of all the resources for every application, and it will clean them up. But if you would, for example, run this in a loop, in an infinite loop, that will be painful. But we want to see it at least once. How do I minimize that here? So now I need to move it again. Right, so here we have our memory unit of the system. Now we will run it. It will call test many times. Test will allocate each time a new memory block, and that will should quickly, yeah, we see already here the memory usage is rising, and we should kill the application. We also see here the usage of this application. We should kill it before we run out of memory. So obviously, if you have a complex application which is supposed to run for hours, and you don't get rid of this memory after you have used it, then at some point your whole system will be slow, because the memory will be used up. It will start paging to disk, which is super slow, or your application might also crash. Although usually the operating system will, on a 32-bit system, it will just crash it quite quickly. On a 64-bit system, usually the behavior is that it will allow it to use up most of the memory, and maybe then it will decide to kill it. So it's much more lenient with regard to memory usage. So what you are supposed to do in your code at some point, would be let's just add it here, would be to tell the operating system that you want this memory to be no longer in use. So you can use vir12 virtual free, where you specify the address. So the address will be gmyint, then we need to tell it the size? I don't think we need to tell it the size. And free type, I don't remember. Let's go with mem3. There is a nice documentation on the Microsoft website to all the different parameters you can have here and their meaning. But just so for a quick demonstration, it's not so important. So now if we run it, okay, it's not working. Why is it not working? We actually allocated even more memory this time. Does it actually need the size? It might need the size, so it would be unexpected, but not necessarily entirely. Nope. I think we have the wrong address. My int. Let's put a breakpoint here. No, that looks valid. The thing is, it might keep some memory allocated so that the next call will be faster. Yeah, now it works fine. So what you could have noticed here also is that, like, if you continue this trajectory, it kind of here would continue and then it would continue again, despite we have killed the application in the meantime. So basically what happened was that it kind of kept this memory just in case it might need it later. And now if we decommit the memory, then the memory will be freed, although I see it here still somehow allocating more and more memory. That is not quite how it should work. Okay, that's the point to check the actual documentation for which function call to use. Okay. Let's quickly check the documentation. So the virtual free is certainly correct, but maybe we have one of the wrong arguments here. So, memcommit. This should be fine. Then it will at some point tell us that we need to use the virtual free to release it. Without a space, virtual free function, and then let's see what we have here. So size. Okay, the parameter must be 0 if we use release, and we didn't use release. Sorry, and we used release and it wasn't 0, so it probably just didn't do anything. Now if we run it, it remains stable. So always read the documentation. Now we see here that the memory is not rising, despite the fact that the program is doing all the time something. So yeah, read the documentation. That's the giveaway from it. And now we can take a look how we could use operating system, C runtime functions to simplify this process, so that we don't have a situation where we have to virtually waste, in this case, 4 kilobytes of memory each time, but how we can do it without it. So the C runtime provides us a function malloc, which stands for memory allocate, where we specify a size, and in the end what it will do is, at some point again, this virtual alloc function is required, but it allocates a much bigger chunk of memory than needed, and then it creates some managerial structures such that it knows which parts of this block have been used, and when you request 4 bytes, you will only get 4 bytes. It will in reality be a bit more that is used, because there is this overhead to manage this memory, but it will not be a whole page wasted. So one thing we can of course do is we can just run the code, so we'll see that it again works fine because it's just allocated memory. We could also take a look how this works internally. Since it is part of the C runtime, it should come with a source code. I hope, or not. It does not come with source code. Load symbols. At least we can see the function names once they are loaded. Once they are loaded, it comes with source code. That's fine. We just needed the symbols. So, well, it just here calls another malloc function, one which is made for the debug use case. Otherwise, it will use the other malloc one. So this allows. So, for example, if you are allocating memory like this, and you are creating a application in the debug mode, then usually when you get a memory block, there will be some memory in front of it and some memory after it, which is filled with a predefined value. And then when you free the memory, the free function will check whether those values have not been modified. Because sometimes if you access one offset too much, then you would modify it. And then if the memory would be directly then followed by another memory which belongs to some other variable, then you would obviously corrupt the memory of your application. If you have this gutters at the beginning, at the end of your memory, then your application will not crash, at least not on its own. But usually when you are freeing this memory, the free function in the debug mode will check whether the values are correct or whether they have been changed by you, and then it will throw an exception on its own, like heap corruption something, which is much better because then you actually know which variable you have accessed improperly, instead of just wondering why some other variable has at some point sometimes a random value. So these mechanisms are quite useful. And if we go step through the whole thing, at some point we'll see the whole implementation, but I think that will take too long. Yeah, that will. Okay, at this point it brings us to some code we don't have, so we will just close it. But the general takeaway here is really that malloc, and of course if you want to free the memory once you are done using it, you just use the free function. Those you can use in any C project because they are standardized. So while on Linux the internal implementation on malloc and free what's the wrong one? Will be completely different. The way they work outwards will be the same. It takes a size. So the one takes a size. Malloc takes just the size in bytes, while the free takes the allocated amount and just returns it. So this is quite useful, and you will probably use it a lot. In C there is also the new operator, and then analogously to it the delete operator, which you can also use to create objects and remove them, which internally at some point just calls malloc and free, but they do much more than that, so we will take a look on that once we start the C++ part. Here the important thing is that we can just simply rely on this malloc being part of any C runtime that we might encounter. And as I already mentioned, there is also a Windows own Windows specific mechanism. So maybe here we just leave this as it was, so that this whole thing is not too difficult, and then we just write a few new samples here. So void mem1, mem2, mem3, so that we see how we can allocate memory. And then once we are done using it, we can free them in an arbitrary order. So we can free 3, then we can free 1. That's the nice thing about this memory management mechanism, is that we can do it in any order we want, and because it works in any order we want, people decided to call this type of memory management a memory heap, because you can just pull out pieces of memory as you need them and then throw them back on top without looking where you are putting them back in. The whole thing does all that automatically for you. And on Windows specifically, you have the function heapalloc, which wants to first know from which heap to allocate to. Should be a default. Let's see what's the documentation says. There is a function that gives you a default heap which has already been created for the application. get process heap, that's the name. So when the application starts up at the very early process startup time, long time before any of your own code starts execution, it starts its existence in the NTDLL, and within the NTDLL at some point a default heap for your application will be already created, and this default heap can be obtained using this get process heap function. Then we can specify some flag, so we don't care, and let's say we can 100 bytes. And this malloc call at some point will internally either give you out memory that it already has, or realize, oh, the whole heap that I already had is full, so it will so the entire memory that it has is full, and then it will return to, call this heap alloc to allocate some more memory for you. Of course, we should not free something that was allocated differently, so here let's call mem hamem or something like this, and we will use a different function to free it. Heap free, obviously. Again, it wants to know from which heap to free the memory. Then it wants flags. I hope 0 is fine. We could check the manual. Actually, we should do that. So here for the first one, heap generates exceptions. This means whether it throws an exception on error or whether it just returns null if the memory allocation didn't work. So this we don't care. Heap 0 memory, the memory will be initialized. This is useful because this will give you it will fill the memory with zeros before you get it, so let's keep that, or let's use that. And heap free, that we don't know, so here we don't need, so here we can just use it as 0, and it will pretty much do the same thing here. Actually, what we could try maybe is we can put a breakpoint here, then see if we where we arrive. So we jump around the get process heap, but we want to call the heap alloc. So as you see here, heap alloc redirects us to RTL heap alloc in the NTDLL. So let's put a breakpoint here, then let's put a breakpoint here, and then let's see where we go. So we have seen that if we enter malloc, we go through some C runtime code, which at some point we didn't have the sources for anymore. So let's see if we just play. As you see, it works. So from here, we invoked malloc, then we went here through different functions for which now it seems we actually even had the source code, but at some point, deep inside the malloc call, the C runtime just resorted to calling the normal malloc that is provided as part of the NTDLL. Also historically, like on really old Windows, like Windows 98 or Windows Millennium, you did not have a NTDLL. It was a completely different operating system base, and there such functions usually resided in the kernel 32 DLL. Here, usually the way it is done, they might still even be imported from the kernel 32 DLL, but then they are redirected to directly to the NTDLL. Although when I think about it, I'm sure this compiler which I am using here is not even compatible with Windows XP anymore. So it is very likely that it will not take this unneeded detour, because it will know that anything it is made for is so new that it will have such a function in the NTDLL directly. Okay, so that's that. Well, the time is progressing faster than expected, so I'm talking too much, but I hope it's insightful for you. Anyways, even those detours about things which are good to know, but you probably will not use directly. But anyhow, last thing to show you with regard to this whole heap management on Windows is that we don't need to use this process heap. What we also can do is we can handle my heap. What was the name for that heap? Heap create. Options 0. Initial size 0. Maximum size 0. We don't care. That should work. And then we can just use heap alloc. I will just quickly copy this. We will copy this, call this mem2, and then we will, instead of using the default heap, we'll just use our own. Oops, that's a typo. Heap. Instead of using the heap that has already been created by the NTDLL and is part of the process environment block here in Windows, we will just use a heap that we have created ourselves. And the nice thing is that if we now just allocate a lot of memory, 3, 4, 5, 6, we can just not deallocate it. Instead, we just destroy the entire heap. Heap destroy my heap. Bam. Nuke it from orbit, so to say. This is actually quite useful and might be a performance-wise improvement, since memory operations generally take some time. Because, as mentioned, if you have a very small memory part, then you cannot allocate entire pages. And what you want to do is you want to have some memory block which you have pre-allocated with your virtual alloc, and then under-divide it internally, and then you need to somehow keep track which part of this memory block belongs to which pointer that you have gave out. And even when freeing the memory, you will be required to update some references and stuff like that. So it will take time. And if you know, for example, that in your use case you are loading a lot of, let's say, single data segments from one huge file, and then you are doing something with your data segments, and then when you are done, you just want to keep the result and you want to dispose of all the individual data blocks that you have loaded, then a reasonable approach here, instead of then having a loop that frees everything and runs for a few minutes or seconds or however many elements you have, you just nuke the entire heap that you have created at once. The important thing, of course, at this point to know is that if you would try to refer to any of this memory after you have freed it, there are two things that can happen. If you are using the virtual alloc and then you use virtual3 and then you try access your variable, that's an instant crash. If you allocate memory either with malloc, which is basically just a disguised heap alloc with the process heap, or with your own heap alloc, when you just use your own heap, when you try to access the memory after it has been freed, then the heap does not know that the memory well, the way it works is you can access it, and in a release build, reading might even work for some time until the heap manager gives out this memory to some other function, which will then do something with it and overwrite it. Of course, if you have this zero memory, then it will always overwrite your memory when it gives it out. But the main problem is that if you have such a reference, let's say you keep reference to mem1 and then you do something, then you free it and then you allocate a lot of another memory, then the memory that you got for your first mem1 variable very likely will at some point be the same, live at the same address in your virtual address space as the memory which the heap manager then gave out to another allocation process. And at this point, when you try writing to your old variable, you will just corrupt memory somewhere in your system. So and the problem with this is that such things don't cause a instant crash, or rather I should say an instant exception, because the operating system does not know whether your pointer is within the semantic of your program still valid, because for the operating system you have a number which represents an address and you are writing or reading to that address, and it's always fine as long as this address exists and is writable or readable if you just want reading in your address space. Whether your access as such was valid or not, within the way your application is supposed to work, the system, the operating system in its entirety, as well as the CPU, none of them have any way to know this, to understand this. So when using memory, it is very important to not try to use memory after it has been freed or do other not reasonable things. So pointers are dangerous, especially when using here like this with memory that is allocated from the heap. They have a lot of potential, as I already mentioned multiple times, to corrupt some memory when using them. And that is why when using C++, it is recommended to use so-called smart pointers. We will take a look on those once we are halfway through C++. And there the idea simply is that you leave the management of your pointers to the STL library, and you yourself are not messing with the pointers. You don't need to make a decision when to free some memory, but by how you are using the smart pointers and the implementation of the smart pointers, they know internally automatically when to free the memory for you. So in this way, you can get C++ to feel to a large extent like a language with managed memory, like C# or Java. But at the same time, it still is just C and C++, and you have all the opportunities to do all the mistakes. So I guess what I want to say is that when using C++, you simply need the right discipline to use the tools that the frameworks give you to avoid unnecessary mistakes. And if you use them properly, then the language is just as good and as safe as any other. It's much faster usually, so managed languages are usually not as fast, so there are advantages of using it, and the risks can be very well mitigated. We could try to set up such a demonstration. So we have here our own heap. Let's call this mem0, and here I will add a mem1, and then I will free m1, and let's also int asterisk mem1 asterisk is equals 1. Let's write something to that memory, to each of the memories. 1 is fine. 2, 2, 3, 3, 4, 4, oops, 5, 5, 6, 6. So right. So we start at this point. We have here our memory. It contains a 1, so we are happy with that. Is that correct? Yeah, that's correct. And then we free it, and as you see, it has already overwritten this value. So if you would try now to use m1, it just contains some garbage. And if we now continue through our operation here, and if we see what address mem1 was, and then we see what we got as mem2, you see we got the same address. So if we now execute writing to mem2 and then try to read from mem1, we read basically the memory which we have allocated here. So, and obviously in the same way, if we would try to write to mem2, then we would corrupt the memory. If we would try to write to mem1 after it has been freed, we would corrupt the memory of mem2. 64 is, by the way, 100 as hex, so it shows us the wrong value that we have put in here. So as you see, it is really easy to see how the heap manager is just reusing memory blocks as we go, and why this is really so important not to free things too soon. So for example, when you have only one pointer and you are freeing it, you should just always set it to null, because then if you would have somewhere further down in your code something like this, then that will crash. It will crash because hmem is null, and null is never a valid address. In principle, actually it could be. So the operating system could give you out. It could set up the page table such that address 0 is valid, but it will never do it. So for safety reasons, the way any modern operating system operates is that it would never give you out page 0, memory address 0 as a valid address. So that one would always is basically reserved as a invalid value, so that you can do it. And I mean, the obvious thing here is that if you made a copy of mem1, mem1b, then you either need to null all of them, or you can still screw something up by accessing mem1b. And while that doesn't crash, that works. So when you so basically this scenario where you really access the variable which you just freed, this is unlikely, people won't do that. But what can happen really easily is that you for some reason assign the pointer to another variable, maybe one that can hold different values, and then at some point you forget that you have freed the memory, and then you try to write to it, and then things go south. So yeah, so that's that. And as also mentioned, with this heap alloc mechanism, you can really allocate huge memory blocks. So we can try this as well. We can just allocate 0. I mean, we could allocate a gigabyte or more. 1, 2, 3, 1, 2, 3, 4. That's not quite a gigabyte, but it's still a large number. So it should be large enough that we should see it. Will it be though? Let's go with 4 gigabyte. No, let's go with 2. It's hard to decide. No, let's go with that. Let's go with 2 gigabyte. And then basically we should see here a jump instantly. Oh, it's having complaint. Alright, we already had this, so let's call it 7. Right, so we don't care for this case. We are here, so here nothing yet happened. And when we run it, as you see, zack, the memory usage spiked instantly, a lot. Also here, is it not showing it anymore? We had the memory usage screen here before, but now it somehow is not showing it anymore. So yeah, as you see, we can allocate a huge amount at once, and it works out just fine. So if you have enough memory, you can really easily allocate large blocks and then use them as a consecutive memory pool to do whatever you want. Okay, I think at this point we are pretty much done with all the easy things about memory management. Of course, since there are use cases where this heap alloc is too slow, and if you, for example, know for certain that you will need like 100,000, let's say 8-byte large memory blocks for your data, then it might be beneficial to create some own memory allocator, so an own heap for which you just allocate in one go a huge chunk using virtual alloc. Or you can be lazy, you can allocate a huge chunk using malloc or using heap alloc, that doesn't really matter. And then this large chunk you can, with your own program logic, subdivide into blocks of the appropriate size, and then give them out much faster than how you would normally give out, be able to give out memory when you would be using this heap mechanism provided by Windows. And the reason simply is because this Windows mechanism is really made to handle any size, any arbitrary size, while you can optimize a lot if you restrict your memory allocator to just either a maximum size, so you can have just, let's say, 1 byte up to 100 bytes and nothing bigger, and also with the trade-off that if you allocate only 1 byte, you still waste the other 99. So you have just a fixed size cell of 100 bytes, and then whenever you allocate memory, you are giving out this cell. If something wants less than the size of the cell, fine, it can just waste the rest, or it will get a error because it cannot allocate more than one cell. You could also try to have like a compound system where you see which size it requests, and then have like a couple of pools of differently sized cells, and then just give out a cell from the right pool each time. At this point it already gets complicated, because when the thing is freed, you need to have thought of some means how you can then know from which pool the cell was taken, i.e. how large the cell is. One pretty cheap and obvious method of doing it is that you just have your cells bigger by the size, by a size parameter, so either by 4 or by 8 bytes, and then the first value in the cell is actually the size of the cell, and then the actual offset that you are giving to your program as the usable offset is the first address after the size. So then when you get your cell back, you just take the address you got back to be freed minus size of your size field, and then you get the address of your size field, and then if you know the size, you know to which pool to return to. So there can be a lot of trickery that you can use like this, and of course here also this scheme especially makes it apparent that if your application using this memory cell would for some reason decide to write to a negative offset, then it would pretty much destroy the size information, at which point your whole memory management fails because it doesn't know what to do. Or even worse, it would fail in a way that it thinks it knows what to do, but it does the wrong thing, and then the whole thing collapses. So such custom allocators are used in production, so this is not a hypothetical, so this is something that people really do, and it really can bring you a lot of performance. In the most cases, you can just find a library that already implements some sort of fixed size allocator. If you want a allocator that can allocate dynamic sizes, then that gets complicated, and usually you won't find a trivial library that will do it for you. I mean, you might find something on GitHub, I don't know. Haven't looked for one, but at least the ones which were easy to find usually just are some sort of fixed size solution. Simply because such solutions are the most high performance, and in many applications you are fine with a fixed size approach. Especially if you are fine with wasting some memory. And in the case of Windows, it will try to be memory efficient. Probably much more in the older versions of Windows than in the modern ones, but I don't think they would have on purpose like reduced the efficiency just to speed up things even more. So the whole limitation that you can handle any size already is like most of the complexity, so there is no point in wasting too much memory to save on some computation in these implementations. Good. I think there is nothing more that I can tell you about memory management that would be within the scope of this lecture. I mentioned these page tables and that they have multiple levels, so this is very much a implementation artifact, and even more than just those things that we see in the disassembler, because the disassembled things, we could write that code, we could do that ourselves, but the details of how page tables work and how they are managed is something that only the operating system is allowed to touch. So unless any of you would intend to write an own operating system, you will not be confronted with page tables, except going past the fact that you know that you can only allocate memory on the operating system level in increments of the page table size. So that's the only thing you need to know. Oh, and the other thing, that you can set protection for the pages, so that you can say readable, writable, executable, or none of the above. But everything that goes past this is for the operating system to do, to handle, and not for you to change. Okay, so that's that. We have about half an hour left. I have not been doing any breaks, so I hope you are not too tired. If you want, we can make a short break now, or we just continue with the next thing, which will be strings, and maybe if we have time, then we can also take a look on this printf function. I think we should have time for that, because this is an integral part of strings. So let me know, do you want a short break, or shall we just continue and then maybe finish 5 minutes early? Okay, if no preference. Okay, if no one says anything, then let's make a very short break for a glass of tea and then we continue. Talking for 2 hours is a bit exhausting. Okay, so let's create yet another project. New project. Yeah, strings. And let's include it closed the other project we had open. I will quickly reopen that because I don't want to forget to upload it to the Moodle. I will just upload all the open projects. Right, we don't need accept, we just need CDIO and maybe Windows. So, as said very early in the lecture, the CPU can only handle this built-in machine types. So, be that say a single character, 2 characters, 4 characters, or 8 characters, or these special types for vector operations, but for those we don't care. So how do we represent strings, how do we handle strings, and so on. And probably in a very obvious way, we just use single characters, and one character just represents one character in a string. And if we have a string of characters, it is just not different than an array. So we have seen arrays of numbers when we used when we had the lecture about pointers, and with a string, it's completely the exact same thing. An array, a string is just basically a array of characters. Char meister. We don't specify a length, and then we can initialize it. That's 1, 2, 3. Then we can initialize it just by putting the string we want to write in double quotation marks. And here, in principle, we can write the string very, very long. There are, of course, limitations. We don't want to exceed the stack size, but the stack size being in megabytes, and we're writing by hand, we probably will not exceed a megabyte. So realistically, strings that you might write will be maybe a couple kilobytes at most. Longer strings, if you want like to programmatically create longer strings, what you just do is you malloc or heapalloc a large buffer, and then you just write programmatically your string. Like if you want to count from 1 till infinity, well, infinity will not quite work out. Your memory will be empty at some point, but you could try to count from 0 to however many fits into a 1 gigabyte block of memory. So that's one way of doing it. Well, let's continue with this. So this sort of initialization, we saw something slightly similar when we have been initializing our arrays there, but instead of using a quotation marks, we use these double brackets, and then we put values in brackets, and those values have been then put into the appropriate positions of our array. So the code above pretty much just does the same as t, a, and so on. Oops. You might notice here that here I'm using a single quotation marks, and this is important. So the way this is defined is that single quotation marks are for single characters, while double quotation marks are for entire strings. And now the very interesting part about the string, actually there is one more hidden character which we don't see here. So here we think, okay, the string is how much? 8 characters long. Actually it is not. Actually it is 9 characters long, because there is the null, and that, like, not this null. This null won't work. This null is the ASCII representation of null, which is, I don't remember, will they tell it me? Yeah, which is 48. We need the actual 0. And the way in C strings are handled by pretty much any simple C library is that these strings are null terminated. Because if we have a string, how do we know how long it is? Sure, at this level we could here make constant len is equals size of, and we would get first of all a typo, we would get our 9 characters, so we know how long it is. But this does not work. This only works with arrays that have been allocated here. If we have a function void printmeister const char stern after f %s comma ptr, and then we want to invoke this function. There's a typo again. And then we try to take this code. I already told that during the arrays lecture, but just that we remember that this will give us the size of the pointer 8 and not the size of the string. And if we try to kind of dereference it, it will give us the size of the single character. So there is no way here how we can retrieve the length of the string. There simply isn't. Full stop. We can do it implicitly by defining that every string must be terminated with a null, and then here, if we want to find the null, the length, then we start, of course, this is 0, and then we make a loop for or a while. We can use the asterisk operator to read the pointer at the current position. No, let's go with a for, because I need a copy. So make a for. We make a copy. Current is gleich pointer and asterisk ptr. So the condition is that this must not be 0. And then if it is, so if we continue, then we don't even need like a loop counter. We just take current plus plus. We advance to the next thing, and here we count plus plus. So if we would run this code, why is it complaining about? That should not be const if we want to change it, obviously. And here a semicolon is missing. So we put a breakpoint here. When we write the code, we did not invoke it. Oh, damn it. That should have been... Nope. That should have been current. Always checking the first value, which is t, will always give you the same result. So that's insanity by definition. And here, the way this works, it counts all the characters up to null, and it does not count the null. So the length is 8. But we know that there would be a one more, so we can add a plus plus here, or we could start with this being 1, whatever we want. But the typical definition of a string length is its length without the terminating null, and there is a function which is provided by the C runtime, like the malloc function or the free function. It's just part, it's in any C library. So as long as you include stdio, which is available on Linux, on your Arduino, on pretty much any C compiler, even if you have a 30 years old computer with a DOS operating system and some Borland compiler on it, it will have strlen, which just takes a pointer to your string. And it does exactly the same thing that we are doing here. It just loops through the string. Why is it complaining? No, it should be fine. It was complaining for no reason. And it also gives us 8. So, obviously, this is kind of inefficient if you have a very large string. If you have short strings, like up to few hundred characters, up to a kilobyte, fine, doesn't matter. A bit more computation, doesn't matter, it's fine. But if you would have like hundreds of megabytes large strings, then this method of estimating the string length is just useless. So plus there is another risk with such strings, that they don't have like a natural end. So if you would decide to write to the string, which you can, you could decide to write to it past the null, and then what? Then you corrupt some memory. So just to demonstrate it, but in a positive way, it's just like an array. For is equals underscore. So here we just replace the space with the underscore. Oops, it's the wrong character. And if we remove the breakpoint and just run the thing and see here, then we see that now our string contains this underscore. So that was the wrong button. So and there is nothing that prevents us from writing to 10. Oh, that's actually fun. Although I think in the debug bit it will not work. Let's write to the index 8, because the index 8 is like the 9th entry, so it is 0. So let's append the underscore to this thing and then see how the string will look. There might be like additional zeros with it. But yeah, so the memory we allocated here just got some additional zeros anyways, so we did not trigger a bug. Memory. Right, so if we do this, then no, actually it should be C. So actually this string should, if we try to read it, charge 10, yeah. Apparently this thing, so the CC value is not a printable ASCII character. It is a valid byte, but printable ASCII characters, actually I'm not sure, is it CC, where does CC fit into the size? So we go to Programmierer, hex CC, yeah, so everything that has like the highest bit in the byte set is not part of the basic printable ASCII character set. And the debugger here is just smart enough to see that it sees such a thing that it just terminates the preview. But the immediate window here just goes until it finds somewhere like here and null. So actually the 09 is \t, so the tab button, and then we had in memory a 0. So as you see here, when reading strings which got corrupted, it's very easy to keep reading and keep on reading, and if you don't catch a 0 but the end of the page, then you will run into a read access error and then your application will crash again. So what is highly recommended is whenever possible not to use C strings, although when you are using C and not C++, that's kind of not easily avoidable. It is avoidable but not easily. And pretty much every library that you get that at least common library that you get that is made for just C will use strings like this. The important thing to keep in mind here is that this sort of strings is now something that is really up to the programs and up to the libraries and not in any way hardware supported. It is just a smart way of using arrays of characters, and that's that basically. So often when you are using strings in C, if you want to like programmatically create a string, so what you would do is you would have some char, let's say my long string, then you would specify a length, let's say a kilobyte. We can add this to initialize it with 0, and then you can use yet another function that is available as part of the C runtime, strcpy, which will then take a destination string, and it will take a source string, let's take this one, and it will just copy the string, and it will just keep copying until it finds a 0 in my string. So if we would have here the bugged code, it would well, we found the end before a kilobyte, but if that would be smaller, then it would start corrupting memory. And actually I'm not sure if the compiler will allow us to do that, because this is not secure, and as you see it does not. So if you have a modern compiler, at least modern Visual Studio, I have no idea how Linux handles this. I should make this bigger. If you try to use a function which is historically known to be responsible for a huge amount of memory corruption, it will just not allow you to use this function. If you really want to, you can take this value here, then go to your settings, projects, properties, I mean, preprocessor, and add this thing here. This will tell the compiler to disable those security warnings, and then it allows you to do it. So you can use string copy, and as you might remember the text before, it would recommend us to use string copy _s, which takes our string, obviously. This one is not safe enough. Yeah, this one is a safe one. Then you have to specify the size of the string in bytes. So in this case, or is it in bytes? Size in bytes. Yeah, 1024, comma, and then you have your source string. So it does not protect you from reading past the end of your source string and potentially crashing if you would reach the end of page and there would be no next page allocated, but it will prevent you from overwriting whatever is next in memory. So I think I showed you a demo where I just overwrote some memory with the array, so I won't repeat that here. But if we would have here some other variable, then this function, this s variant, will prevent us from overwriting. It will just terminate the copy, and I think it will return a error code, error number, indicating that it could not copy the entire string because the output buffer was not large enough. And by now, for pretty much every single unsafe unsafe C runtime function, there is a _s variant which is safe and will prevent you from breaking your memory. Okay, so what else do we have? We can, for example, add some string. So we have copied already some string here. So we could use another function strcut. Understream cut s. So cut is short for string concatenation. So like they wanted to call it string concat, but then they were lazy and just called it string cut. And what it does is it first goes through your string and looks for the 0. Obviously, it does not go past the length that you told it that the string can have in total. And then once it found the 0, it will at this point start overwriting your string with whatever you provided here as a second argument. And again, it does not safeguard against exceeding the second argument, but as said, this can only cause a crash here and there and not corrupt memory. So things that causes a crash are not the worst things. The worst things that can happen is if you corrupt memory, because then you will get random behavior and a unexplainable crash somewhere far later. So we can quickly put a breakpoint here, run it, and then we see that our string now right, we broke the string. So actually it did something funny. So it took the string, it filled it with these values, then here there is this tab, and then it added what we wanted it to add. So let's remove our breakage of 0 of the null terminator, and then it will of course work correctly. So it just adds space. Actually, we don't need the space. Or maybe we do. I don't care. Let's leave the space there. It adds space and then 4, 5, 6. And then of course you could repeat cut something and cut something and cut something else until you are done creating your string. And this is quite useful. For example, you can have like a folder. In the folder you have a file name. The file name then takes a number which you count through, and then you have a file extension, and you want to make one string containing one file name in one go. So this string copy and string cut is quite useful. Of course, the most hacky way how people would do that, if they really don't care for security, would be string copy. Then another string copy len from the previous string, and then have here our 4, 5, 6. So they just string copy the beginning of the string. They then take the beginning of the string, count the length of the string, add it as offset, so they move to wherever it ends, then they overwrite it again with string copy. So I mean, internally that's not different than what string cut does, but that's the even more hacky approach. So don't do that. And the reason why I'm commonly demonstrating all these bad things is because sometimes people may think, oh, I will do it this way, this is so smart, and so on, and they might not realize that this why it might look smart is actually, it might also be very smart, but it's also a very dangerous thing. So if there are documented ways of doing things the safe way, by now with regard to C and C++, it really is highly recommended to always do the things the safe way. If you really know that at some point it is performance critical in some single function to do the things in the most hacky way possible, and it's a very small piece of code which you will analyze and think about it and sleep about it and then think about it again, then sure, go for it, optimize your code, let it do things the dangerous way, but don't let your code do things the dangerous way in places where it's not performance critical. And for most parts of your code, it won't be. Nowadays, we have so much performance, we really need to optimize only where it really counts. And there is a large list of functions which you can use with strings. You can find them on the CPP reference documentation. So no, that's not here, it's somewhere else. Where strings age, strings handling. Okay, here is the list. Nope. So we have all the functions and the safe versions of those functions listed here. The CPP reference.com is a really good resource to look up all the things that are standardized. Everything that you learn from this site will work on Windows, will work on Linux, will probably work on the Arduino. Although some Arduinos have really old C, this here is like always the new version. It also, by the way, it also tells you if the more complex things, like here, only available in C30, sorry, in C23 or in C11, and so on. So, in an Arduino, I would expect all the everything that's newer than C99 to maybe not work. But for any modern Visual Studio or GCC compiler on Windows and Linux, all those functions, I mean, to be honest, I don't think C2023 will be supported by Visual Studio 2019, so that won't work. But C11 is, I think, available in probably even in the Visual Studio 2015, since they had by then 4 years time to implement it, so that should be good. And if I recall correctly, we have like C11, C7, C13, C17, and C23 is like probably no one implements it yet because it's so new. We can actually take a look on which C variants are supported by our Visual Studio by default, and we see here we have 14, 17, and 20. Oh yeah, I forgot about C20. C23, of course, it does not support. Probably the next version of Visual Studio might support it. It's likely it will. We will see. Because Microsoft, sometimes they don't immediately implement the newest standard, they just wait one generation, which is reasonable. Or using the newest things usually just is asking for finding the newest bugs, so it's not really recommended. The next thing that is good to know, I will just copy in here. These are the escape sequences. I just copy it from somewhere here, just I have it open on the host. So as I already mentioned here, when we have corrupted the memory, we saw that at some point we have this tab which was \t, and when thinking here about strings, you might have already wondered, okay, so if I am supposed to start and stop a string with a quotation mark, how the heck do I put a quotation mark in here? I mean, it complains, it doesn't work, it cannot work, it could never work, because how could it? So the way to do it is to use this escape sequences. So let's call it mystring2, and the idea simply is that you put the escape character, so the \, and then you have a list of special characters which have but some of them do kind of what they say. So like a single quotation mark gives you a single quotation mark, a double quotation mark gives you a double quotation mark, just that it will not break the passing of the string. So when the C compiler passes the string and it encounters this escape character, then it knows that if then a double quotation mark comes, then it is not the one that is supposed to end the string, but it is one which is supposed to be encoded as part of the string. Actually, single quotation marks work. They don't complain because it kind of knows, okay, this started with a double one, so a single would not be a valid termination anyways. You can use the escape sequence for them, but you don't have to. And for example, in this case of initialization, we could in principle put a we could put a double quotation mark into this, and then we would have like two double quotation marks, and it would also work without a escape sequence. So there are ways around it, but the recommended way is to just use the escape sequences. Well, question mark is kind of a question mark works just fine. So not all of the escape sequences which are provided in the list really are necessary. But for example, if you, and of course if you want, so if your backslash means something, how do you get, for example, a path? So let's say we have a path. Char my path is equals c double punkt backslash dos/run. And obviously it says, okay, backslash d does not exist and backslash r is something else. What the heck is this supposed to be? This obviously is wrong, and the simple way to fix it is just use double backslashes. Right, I forgot this thing. So the way this works here is that you just escape the escape character to get a single backslash. As simple as that. It also is specified here. And then we have a list of, well, this one doesn't have a reason, that would work just fine without it. You can use \0 to actually put a null inside of your string. So for example, we can have like test \0 1 2 3, and now if we add this thing here, we just want to do it with this, and we would put a space there. So if we now put the breakpoint here, so first if we try to look how this looks, it is just test, and I mean the compiler knew that there is more going, so that is not the best test. Let's just char asterisk this thing so that it doesn't know, because when we really use the variable, it really knows how it was defined here, and then it's cheating. But if we just cast it to char, then it drops that information and just says, well, that's a string, it's test, it ends here, and if we would now string len it, it would tell us it's 4. But if we replace this null now here with a space, then if we repeat the same test, it goes past it, and then it's fine. So this mechanism, this behavior that you actually can put a null in a string, this is sometimes exploited by some APIs. For example, if you would want to pass a list of strings to something, how would you do that? You could of course have an array of pointers which point to individual strings, which is cumbersome and requires more memory. So if you try to be super smart, you could say, okay, I will make a list of 0 terminated strings, and the way to terminate the list will be to have 2 zeros one after the other. So basically, by definition, your list cannot contain a empty string, because as soon as it encounters the first empty string, it means the list is terminated. The other way would be that you just say, okay, I will make it null terminated, but I will tell the function which I'm giving this as a variable, a second variable which tells it the length of the string, or maybe even the count of entries, whatever feels more secure. Obviously, count of entries could be wrong, so the total size is the safer bet. And then it will just stop, not at a second 0 character, but it will just stop once the length has been entirely consumed. So this is one thing you can do here. And of course, then to the last set of characters. So a bell is like a super historic thing. Like when you had real printers, they could not just print, but they could also make a sound like ding, like really just hit a bell. And for that there was a special control code. I'm actually not sure what Windows would do. I think if you print the bell with printf, Windows will actually make a sound. Backspace is again something for the console, so that if you have a console open and you, well, this one doesn't work because it's suspended, and now it's terminated. But if we open a console which is actually waiting for our inputs, if we write something and then hit backspace, we could, if you print something internally, like with printf, you could then with backspace clear the characters back from the screen. So you could do that with printf. \f is like page feed, so it would move the paper in the printer by 1 page. \n we already used quite a few times, for example here somewhere. \n means new line, but it does not just mean new line, it means actually line feed, meaning move by 1 row. But on Windows, or at least on old Windows, and definitely on DOS, it would not move the cursor back to the beginning of the line. On Linux it always did this as well. This is why on Windows the customary way to get to the new line is carriage return, which is the next one. So move the carriage back to the beginning of the line and then line feed by 1. So as you see, the old printers were extremely basic. They just did exactly what they were told. They didn't do anything extra. So you needed 2 characters to actually line feed. Also, there is a utility to this, because sometimes you might write some text and then move down, then move a space and then write some other text. So it in a way is more efficient than if you write a text, move down, move back, then put a lot of spaces to move to the position where you want to be, and then keep writing the text. So there is a good reason why historically those things were made this way. \t, as already mentioned, is a horizontal tab, and \v is a vertical tab, which I have no idea where that would be useful. So it pretty much just means that it will move vertically, not by like one space or in this case one line, but by multiple lines. Apparently that's useful for something. And pretty much that's it. And the last thing with regard to these escape character sequences is that you can also, in case we would want any non-ASCII character or something that is in some way special, I have no idea what we would want, but we can demonstrate it with something else. So we can here have \x, and then we can provide, so we can have \, and then a number, then it's a numerical value like in base 10, \xnn, then it's a numerical value but in hexadecimal. So if we know that, what did we say? What value does this have? This has a value 95. So let's just \95. This go this backslashes we will leave. So this we will comment out. So if we run it now, then we will see that we have just a we just have a what didn't work? Backslash. It should work, but it didn't. It just wrote \95. Sorry, it should be an octal. And 9 obviously is not an octal. I should read my own documentation. So let's find out what 95 this one doesn't have the right calc. Let's I'm seeing we are running out of time, so we'll need some more time next time. So decimal 95 hex is a 5f. 5f. And now if we run it, then we will get our underscore. So as you see, you can now really provide any value you want. And since we are running out of time already, then I don't want to keep you longer than you have to. We will continue strings next time before we continue with the other things. Maybe I will not upload strings to Moodle since we are not yet done with that one. That's why I will upload the next time. I just wanted to show you one single thing, namely, you might have noticed that here we only have this printable ASCII characters, so only American text basically. So what do we do if we want to print some Chinese text or some other text, some Arabic text or an emoji? We use something that's called a wide character, like wide, like it's wider, it has more bits, underscore t, and everything else about it is like my Vesta is like with the normal with the very normal strings, just that the strings start with L for long. And now every character is not a byte, but now every character is a short, meaning it has not 256 values, but 32,000, no more, 64,000, yeah, 60, almost 65,000 values, or maybe in excess of 65,000 values. It has a lot of values. So this is pretty much enough to cover most of what one would want to cover. But of course there are special cases where even this would not be enough. In this case you can even have a compound character, which will be made out of two wildcard characters, and you can use this notation. So this notation here, UNNN, would be a Unicode hexadecimal encoded value. And of course the next thing, this sort of encoding is called Unicode, because it's like an universal encoding for all of human language at the time. And given that you can not only have like single Unicode character, but also have Unicode characters which are made out of actually two white characters, this gives you then basically a address space of 4 billion. So that's not exhaustible. Then you could invent a new word every second, and it will never finish inventing new words. So in this case, here this particular compound Unicode character is a smiley face, and this is quite nice because this way you can put such things in your text without having to have assets and graphical resources for all the smiley things. And there is quite a lot of other things that you can print. You can print arrows, vertical lines, different lines, hearts, sad faces, whatever you want, or maybe not whatever you want, but you can choose from a very large set, and you can Google Unicode to find a non-exhaustive list of all the different Unicode characters that are possible on the Wikipedia. And the modern Windows operating system supports Unicode pretty much everywhere, so you can even in principle put such things into file names. And that's I think a good moment to stop for today. As mentioned, during the next lecture we will continue with this printf and how to create more complex strings, how to convert numbers, like proper numbers to a string, which is non-trivial because you need to convert like every position in the number, and the string length may even vary. So if you have like the number 10, then you don't want like leading zeros, you just want 2 letters. If you have the number 1 million, you want it to take 7 letters, and so on and so on. And then we'll also take a look on how strings can be made safer. But as said, for today, that's it. If you have any questions, I guess write them by email, because I think Dadas wants to finish for today. You can ask, of course, any other question next time. And yeah, and that's it. I will upload exceptions and memory to Moodle. Strings we are still working on, and I will upload the recording as well, so that you have all you need. We did not arrive at a point where I could give you some homework, but I promise you will get some exciting homework next time. Yeah, that's it, and have a nice weekend or a nice Friday, depending on how your schedule is, and we will see each other, I guess, next week, unless next week is a holiday, but I don't think so. What does my calendar say? April. No, next week is a normal day, so I think we will see each other next week. So, bye bye.